since Professor Lee went to a conference meeting, I will take his place and teach you guys about self-supervised learning and PINN. So I will mainly focus on the coding example that Professor Lee just briefly explained during the class. So for the first part, I will briefly explain about the self-supervised learning and go over the coding example mentioned during the class. And also I heard that Professor Lee has finished basic concepts of the PINN, so I will just briefly demonstrate those coding examples that were in the lecture note. So let's start our self-supervised learning. So Professor Lee has already finished talking about self-supervised learning. So self-supervised learning, what technique have you learned to use when you have very small number of data? Perhaps data augmentation or transfer learning like this. So transfer learning is very important because it is very useful when you have just small number of input data. So by pre-training a network with big data like this ImageNet with labels and fine-tuning it for your task, you will be able to achieve the high accuracy with small number of data. So this ImageNet is a basic, very famous example about big data that was labeled by many humans. So it took like several years to label this total big data set, but this labeling the total big data is very arduous, and we want to use unlabeled data set for the transfer learning. So self-supervised learning uses these concepts, the concept of transfer learning. So we want to pre-train the network with unlabeled data set because we have more unlabeled data set in the internet. For example, like in Facebook, Instagram, or Twitter, there are like tons of images that are unlabeled, they're flourishing into the internet. So the self-supervised learning just want to use those kind of unlabeled data to pre-train some kind of network. Because the more data you have, the more profound or like well-performing network you can get for the transfer learning. So basically, the self-supervised learning just wanted to use those unlabeled big data to pre-train the network so that you can use it for your task like image classification or object detection. So this is like basic summary about self-supervised learning. I'm not going to talk about details about concept of self-supervised learning because I heard that Professor Lee has already covered it. So in short, self-supervised learning is a way to supervise the learning using labels generated from data without any manual or weak label sources. So in other words, so the self-supervised learning use special labels that can be automatically generated from the data itself. So this kind of self-supervised learning, we have two kind of main strategies. First, pre-training task and then downstream task. So for the pre-training task, we call it pretext task. And for the downstream task, it can be any like image classification, object detection, segmentation, and anything that is related to the input data you used. So for the pre-training task or pretext task, you use the self-supervised method in the pretext task. So as I mentioned earlier, so yeah, self-supervised task is composed of these two basic steps. So in the pretext task, we want to learn the general features of the images. So why we use self-supervised learning again? So we want to use unlabeled data that have like large number of data set. So we want to basically learn the image features in the pretest task and just transfer the learned knowledge to the downstream task so that we can perform the knowledge transfer as written here. So the pretest task is same as the pre-training part of transfer learning, but this time we pre-train the network with unlabeled data set, unlike the transfer learning cases. So in your homework, I believe you used VGG16 model that was pre-trained by ImageNet. But ImageNet is, as I told you again, is labeled data, and this labeling takes too long time. So this basically using unlabeled data, which we can collect very easily and learn, and we will use those unlabeled data set to train the pretest training process, and so that we can extract image features from the pretest task. So with well-defined pretest task, we will be able to create a network that is well-trained to extract the important features of the images. And the downstream task is just the final task you want to perform. So in many cases, this kind of downstream task is simple image classification, or you can just use it for object detection or even the natural language processing. So this downstream task can be various tasks that you want to do. So I heard that Professor Lee has covered all the basic pretest task methods, like this image inpainting or image super resolution and image colorization and jigsaw puzzle and the context prediction. So there are many pretest tasks that you can use to extract features from the images. So today, for the coding example, I'm going to use the rotation network. It's defined here. Okay. So, any questions about self-supervised learning basic concepts? Was I too fast or something? Okay. So, with images that do not have any ground truth label, we can generate temporary labels or fake labels, you can say, by rotating all images with fixed angle and labeling them with the number of rotation you made on the image. So this figure explains the basic concepts of the rotation network. So the fixed angle we will use for each rotation is 90 degrees. And when you didn't rotate the image, we will label the image as 0, like the first case. And the second, if you rotate the image 90 degrees for just one time, then we will label it x as a y equals to 1. So labeling as a 1, and 2 and 3 and 4, or 3 and like so forth. So if you rotate the image for 270 degrees, like 3 times for the 90 degrees rotation, then you say y equals to 3. So with this kind of simple rotation, you can get the label of each images, and you can use this label to train the network. So self-supervised learning is supervised learning, but the label is not the ground truth label you usually have, but the labels are just the fake labels that you can generate from the image itself. Okay? So someone might ask why we use 90 degrees, why not 30 or 60 or like 220? Then the author of this genre have tried various types of angles, but they said that rotating 90 degrees was the best performing degree they got. So basically, rotation network is a pretest network that is used to extract important image features from the images, given images. Okay, so so we will use this rotation network as our pretest task, and downstream task is to classify the MNIST image dataset. I believe Professor Lee have already explained about this coding example, but I want to make sure that what kind of dataset we will use for each step so that you're not being confused. So this is this is basic summary about the data we'll use for each task. For the pretest task, we use 10,000 MNIST images without labels. Because pretest task is the key to the self-supervised learning, we don't use labels. And also for the downstream task and supervised learning task, and I will explain about supervised learning afterwards. But for the downstream task, we use 1,000 MNIST images with labels. But I'd make sure that these two kind of image data sets are not overlapping, because we do not want this pretest task and downstream task to share the same image. So I split the MNIST data set so that the pretest and downstream task do not share the same image. So pretest task is about 10,000 MNIST images, because the key point of the self-supervised learning is to use large number of unlabeled data set in the pretest task. So I just gave 10,000 images, which is 10 times larger than the images that downstream test gets. So you might wonder, hey, MNIST dataset have already labels, but I know that, but just assume that we do not have labels for that 10,000 MNIST images for the pretest task. So normally, we don't use the same MNIST images dataset for the pretest task and the downstream task. Usually you used random images that you extracted from whatever, the Instagram, Facebook, Google, or something like that. It will be like tons of images. And for the downstream task, yes, you can just do the simple MNIST image classification. So pretest task is normally use more data than the downstream task. And the pretest task images do not have labels, while the downstream task images should have labels. So downstream task and supervised learning task will have the labels for each image dataset. So as I've said before, self-supervised learning is composed of pretest task and downstream task. Then you might ask, then what is the supervised learning for? So I'm going to say that supervised learning is just for the performance comparison. So we want to compare the whether the self-supervised learning, or AKA as a pretest task, performed or extracted good image features or not. So by evaluating the performance between the downstream task and supervised learning, we can find out that pretest task successfully extracted important image features or not. So for that case, for the downstream task and supervised learning, we use the same training data set and the same test data set. So I'm going to explain the details about downstream task and supervised learning afterwards. So let's begin the coding. So after we define the data set we will use, we will first rotate the images. But before that, I'm going to briefly explain about the codes here. And I'm sure the importing libraries is like piece of cake right now for you guys. So I'm going to start from this loading MNIST data set. So this loading MNIST data set codes can be quite ambiguous for you guys. So I'm going to just talk about a little bit. So this simple X train and XY is used for the pretest task. And this X and Y test is also used for the pretest task. However, as I mentioned earlier, we don't use labels for the pretest task. So you can just ignore this Y here because we don't use ground truth labels for the pretest task. And this XX and YY train, the image data sets are given to the downstream task or supervised learning task afterwards. So this XX, YY is for the downstream task and X and Y are for the pretest task, but we don't need this Y in the pretest task because pretest test is just for the self-supervised learning, so you don't need a label. So the shape of each data set is given here. So as you know, MNIST data set is in size of 28 by 28. And as I said before, we will use 10,000 images for the pretest task and 1,000 images for downstream to train the downstream and the self-supervised learning, and 300 images for the testing. So as I defined the basic data set we will use, we will now have to rotate the images so that we want to make the self-supervised learning going on, okay? So after rotating the image, we will have to set the labels. So if you just rotated the image in 180 degrees, then you need the label y equals 2. So this kind of basic steps are written here. So I'm sure that one-hot encoding is now familiar with you. So I'm going to just mention about this rotation 90. So this rot 90 in the numpy function is just basically just rotating the image into 90 degrees in anti-clockwise, okay? So let me make bigger for you, okay? So this rotation 90 means you're going to rotate the image in 90 degrees in the anti-clockwise direction. And this k is equal to the number of the rotation that you will perform. So if k is equal to 1, you're going to rotate the image 1 time. If the k is 2, then 2 times, and 3 for the 3 times. So 3 times 90 is 270 degrees. So 270 degrees rotation, 180 degrees and 90 degrees. So rotation 90, it is a function defined in NumPy, so you can use just simply like that. So if you have right now defined a new data set which calls X rotate and Y rotate, and each images is just composed of a rotated image and its label. So if the image is not rotated, then the label will be 0, and if you rotated the image into 90 degrees, and you will get the label of 1. So we will use this kind of X rotate and Y rotate data set to train the network and the pretest network. So the final result of the rotation is like this. As you see, the image is rotated in the counterclockwise direction. Now let's build we will define the rotation network for pretest task, and we will train it. So this model here seems very simple to you, right? So we have used convolution layers and max splitting layers for many times. So this kind of specific settings might be very familiar to you. So basically this pretest task, also called as rotation network, is composed of 3 convolution layers and 2 max splitting layers and a dense layer at the last. So remember, we need to classify 4 different rotations. So at the end of the dense layer, we want output as a 4, okay? So for the MNIST data set, because we have 10 digits, the output dimension of the total network should be 10. But because we want to classify 4 different rotations, so we use the unit equals to 4 at the last layer. So into summary, so we have 3 convolution layers and 2 max splitting and a flatten and a dense layer for the rotation network. So this rotation network itself is also defined by the author of the journal, and they have claimed that using 3 convolution layers extracted images very well. Image features very well, okay? So if you have trained the pre-trained task, pretest task, and we want to transfer the learned parameters to the downstream task. And before that, we need to train the model we defined above. So training is also very familiar to you. So optimizer, we always use Adam optimizer, or sometimes we use stochastic gradient descent. And for the loss, because it is just simple classification, we use categorical cross entropy loss. And this fitting problem, it is very simple, and it is very obvious. So I'm not going to explain details. So after the training stage, the most important thing for the pretest task is here. So you need to, after the training, you need to make the model of the pretext as a false, train of a false. So you will not going to train the model even if we call the model to train, okay? So even if we just call the model and hey, this is new data, train this. But we will not, the model will not going to be trained because we already set the trainable as false. Okay? So we are just freezing the network itself so that we can just simply use it for the downstream task. This is this is often used for the transfer learning techniques, so it can be familiar to you. Okay. Any questions? Okay. Now it's time to build a downstream task. As I said, downstream task is kind of is use the pre-trained pretext network and fine-tune it for your specific target task. So we're gonna use the get layer method in order to make the knowledge transfer from the pretest model. So as you see, this is a model pretest that we already trained before, and we already set the parameters to be not trainable. So even if you just use these layers in this kind of model, the layer parameters will not be trained. Okay, so we just bring on the freeze layer that will not train. Okay, so what is this index? This index means the index number of each specific layer in that model pretest. So for example, this layer has an index of 0, 1, 2, 3, and so forth. Okay, so by calling the index number, you can get the specific target layer into your new downstream task. As I said before, because you already set the pretest model untrainable, so this is just getting this layer is just getting the parameters that have already trained and will not be trained anymore. So after getting 4 layers from the predefined or pre-trained models, we will use only a single layer. This single layer is only trained, okay? Because our downstream task was to classify the MNIST image dataset, the last output of the layer will be 10, okay? Because there's 10 image in the 10 digits in the MNIST dataset. So as you can see down here, the basic structure is very familiar to you, yeah. But the 4 layer at the top is untrained, okay? Because we already have trained parameters. So we will not train these parameters, but we only train this last layer so that we can perform our task very well. So as you can see here, there's a total parameters of this number, but there's only trainable parameters for this layer, okay? Because we already freeze the upper layers. So there's like only 2,000 parameters to train. And the training step is similar, but I use another optimizer other than Adam to show you guys. So we use the stochastic gradient descent optimizer. The stochastic gradient descent is learned before the midterm exam, I guess. And loss is a cross entropy loss, okay? So everything might be familiar to you, but validation split is simply splitting the data set, the training data set, into the train and validation set so that you can validate the training process more easily, okay? So usually you have to separate the image data set or data set before this step, but with this validation split, you can just automatically split the training data into like 0.2 means 5 to 1, okay? And epochs, this is very easy for you. And we use new thing, this callback. So callback means this callback function is for the early stopping function. So early stopping means you can set what you're gonna monitor. So I set the accuracy. So this means that I will monitor the accuracy, and if the accuracy goes down for the 7 times, I'm gonna stop training, okay? Then why do we have to use these callbacks? It's because we want to prevent the overfitting problem. When the model starts to overfit, the accuracy will go down and so on. So we're gonna set this monitoring accuracy, and we will give the patients of a 7. So you don't have to use accuracy to monitor. Usually, many people use validation accuracy because validation accuracy is basically the test accuracy. So you can use validation accuracy or validation loss if you want. So anything you can go on. And also the most important thing, for the downstream task, we have labels, okay? So we use both training labels and the training image data set, unlike the pretest task. Pretest task also had labels, but their labels are just fake labels that are generated from the image. Now this label over here is the ground truth label that we know, okay? So after the training process, as you can see here, the epoch ended at 29th step, although we have set 50, okay? So this means that after 29th epoch, the accuracy has decreased for 7 times, okay, beforehand. So the training process stopped automatically because we know that it is fully trained, okay? So let's check if our downstream tasks are trained well, okay? As you can see, when the downstream task given an image like this, and this classifies very well, okay? So we have known that downstream tasks are trained or performing very well for the MNIST image classification. So downstream task is basically similar to the transfer learning. I know that you have already solved the homework problems related to transfer learning. In the transfer learning, you just get the pre-trained weights from the VGG16 network and use for the, what was the question? The Berry classification problem, I guess. And the classification accuracy was very high. And this is the same. We just use the self-supervised learning to pre-train the network, and we use that pre-trained network to classify the MNIST image data set. So basically, the transfer learning and self-supervised learning is quite similar, but self-supervised learning uses unlabeled data set for the pre-training step, okay? This is very similar. So now we want to compare our performance of a self-supervised learning with supervised model. So this is basically comparing the transfer learning model and non-transferred model, okay? So this is like downstream model and supervised model. These model structures are same, and the train and the test data are same as well. However, in the downstream task, you have obtained these pre-trained parameters from pre-test task, while in the supervised learning, you're going to learn every parameters in this case, okay? So we're going to compare these two so that we can prove that this knowledge transfer is better than just training all over again, okay? So basically, for the supervised learning, I defined the same model structure with the downstream task, okay? So the model is composed of 2 convolution layers and 2 max pooling layers. So as you can see, so in the summary, the model structure is same as the downstream task, but at the downstream task, only the last layer was trainable. However, for the supervised learning case, all parameters are trainable and none are non-trainable, okay? Because we don't use pre-trained layer, we just train it all over again, okay? So we're going to compare these 2 networks so that we can prove this knowledge transfer or self-supervised learning performs better than just supervised learning, okay? So for the optimizer, I'm going to use the same optimizer and same loss function as we used for the downstream task, and also the same data set for the training, and rest of these parameters are also same, okay? So after a few steps of training, we could test our models. So we just, first, this is the self-supervised learning accuracy on the test data set was 86%, and on supervised learning on the same test data set was 75%. So there is 11% difference in accuracy, so I guess the self-supervised learning performed better. However, this is just simple MNIST image classification, so this was like not that like there's no big difference between these 2 accuracies, but I guess if you use like unlimited images for the pre-test task and use it for the downstream task, I mean it can be reaching 100% because you have unlimited images in the online, okay? Or unlabeled data sets are almost unlimited, okay? So we have done the coding example for self-supervised learning. Any questions? Okay, no questions for self-supervised learning? Okay. So I guess you guys understood coding very well. Okay, next is physics-informed neural network. Professor Lee told me that he already introduced about basic concepts of PINN, and I'm here to just demonstrate the codes that were introduced in the lecture. And Professor Lee told me that he already defined the questions that we will solve in this practice. So I'm going to go straight forward into the coding examples. So let's start with a simple example. So physics-informed neural network is basically we're going to inform the physics into the neural network. However, I know that many of you guys do not have their backgrounds in the physics or mechanical engineering, so I'm going to consider that, and I'm not going to discuss about details about the physics and mechanical engineering. So I'm going to just basically explain the question we want to solve here. So if we have that ODE equation or differential equation like this, and initial condition as given as below. If we have those two, we can get the exact solution by your hands, simply because this is just a simple question, right? However, we want to train the neural network so that we can predict the exact solution with given ODE and initial condition only. Okay. So why do we use this PINN if we can just find the exact solution with hand? Yes, we don't use this kind of question, but it is just a simple demonstration for you guys. So that this kind of PINN can, PINN, which is physics-informed neural network, can solve this kind of ODE problems as well, okay? So this first example is very simple. So because the problem is very simple, we will use just one hidden layer. So just one hidden layer with 32 nodes. So when the time t is given, we want to predict the u, right? Because we want to find that exact solution, right? U and t relationship is the key that we want to find. So if the time t is given to our network, we want the network to predict u. However, how can we update the loss if we do not have the truth level, right? So in order to get the truth level, we will use auto gradient defined in the TensorFlow. So this automatic gradient is performed to get this dt of du. So remember that we do not have this exact solution. We do not have this exact solution. So even if we have just find u, we do not know what to compare with this, with the predicted value and the truth value. So this means that we don't have any ground truth values to compare with the predicted values. But we do have the truth value about dt over du. So we need to compute the gradient of this predicted u so that we can compare to the truth level so that we can learn the network. Okay? So two loss function will be used for this. So ODE loss and second is initial condition loss. So after we get u from the model and we perform auto gradient from the TensorFlow, then we can get this dt over du. And we already have shown that we already know that dt over du equation is this. So we're going to compare the calculated dt of du with the already known ground truth, and we will use this MSE error for the loss function. So PINN is basically physics-informed neural network is basically just modifying the loss function. Okay, neural network style is very similar, just one hidden layer, or this is ANN, the simple ANN, but the loss term is very complicated, right? So loss function is the key for the PINN in my perspective. Okay, so initial condition is given as u0 is equal to 1. So if we get this u and if you plug in t equals to 0 into this u equation, that we want this MSE loss to be 0. Okay. So adding up this ODE loss and initial condition loss, we will get the total loss. Okay. By just looking at this diagram, you may be confused. So let's begin our coding. So before we start the coding, there are two methods you can do. There are more methods, but I will explain about two famous methods to solve these PINN problems. So first method is to use the TensorFlow models as you already used for this semester, okay? So we can just use TensorFlow for the physics-informed neural network, but it's quite complicated. So there is a newly defined library called DeepXDE, which is DeepXDE is a specific library targeted for the PINN. So when you use this DeepXDE, it's much simple. So today I'm gonna show you how to code this kind of problem with TensorFlow and also DeepXDE, so that you guys can compare these two algorithms and just use the whatever you think it is comfortable. Okay. So let's start with importing libraries. So importing libraries is very simple, TensorFlow. Okay, and we need to define the network. But as I said again, just simple network with one hidden layer. Simple, right? So I'm not going to just explain about the model here. Okay. And for the optimizer, we use Adam optimizer as we used before. And this loss ODE system is the key, I think, key to the to this problem. Okay. So this ODE system in the function of ODE system, as you can see, you're going to define some parameters that you're going to use, okay? So why do we use this gradient type, okay? In the TensorFlow, when you do the gradient, then the previous gradient is just automatically disappear, okay? This TensorFlow uses this gradient function, then the previous gradient information is disappeared, so we want to use gradient tape so that we can record all the gradient values that we have calculated before, okay? So basically these TensorFlow models, we use gradient tape to watch over the gradient values that we have already get. Okay? So this ODE function will get two things as an input. T is a time variables, and net is a network that we're going to use. So network is already defined above, so we know what is the network, okay? So this U under T is a du over dt. So the problem that we want to solve here, so this kind of du over dt. And this ODE loss is also, I previously defined ODE loss. So when you get from the model the information of dt over du, then you can just compare these two and find the loss. Okay, this is the ground truth label that we had, and this is the du over dt equation that our model will predict. Okay, so our model gets u, but after getting u, we need to compute the gradient, right? So this gradient stage is automatically done by the TensorFlow. However, we want to record these gradient steps so that we can use for the arrow back propagation. So we use the gradient tape, okay? So to record the gradient values. So the initial condition loss is also simple. So initial condition was u0 was equal to 1. So if we give a network of a t0, which is t is equal to 0, right? Then we want the network in ideal condition. We want the network to give us 1, so that initial condition is fully successfully met. So that we define the initial condition loss like this, okay? And for the square loss, because we defined the mean square loss, we're gonna just square each losses and make a mean of each square losses. So this is defining the total loss that we're gonna use for the training the model. So as I said again, physics-informed neural network is just a neural network with very complicated or physics-informed loss term. So the loss term is the key to the PINN. So this is mathematical issues might arise, but just simply think that this is the ground truth label we have, and this is the model predicted label, and we just compare these two. Then why do we need to get the gradient? Because we do not have the ground truth label for the exact solution, just we presume it, and so we need to just do the gradient thing with the TensorFlow. So this is just basic steps to define the loss term in the function. Okay. So let's train and predict. Let's train and predict whatever we wanted to. So for the training time step, we're gonna choose randomly 30 points for the training. It means that we're gonna just randomly select 30 points for the training process. So basically, you can just think that 30, there are 30 input data. Okay. So this randomly chosen 30-day training point will given into the ODE system. We will able to get the training loss. And with these training losses, we will perform the error backpropagation. So these two lines seems very complicated, but you can just think as a step for the error backpropagation as you learned before. So this is very formulated equation, I guess. So after the training stage, we can draw the loss curve, and loss curve seems to be performed very well. And let's see our result. So we have trained. These dots are the training points, and these red lines are the prediction of our physics-informed neural network. This tells us that even with just 30 randomly selected points, we actually found the exact curve for the entire test data sets, okay? So even if I said this training data set, but it is not the original training data set. This training data set is actually often called as a collocation point because we do not have data in this case because so let me explain details. So we have these two, right? And we want to find the ODE loss, and we want to update the ODE loss and initial condition loss with these two equations. But if we have time t, we have dt over du. So we know the value if we know the t, okay? So this is why we don't call the training data as the training data, but it is called as a collocation point. It means that if whatever t is given, we know the value of the dt over du. So it is not that training is not called training, it's what called collocation, okay? So just remember, any t can be used for this kind of example because we know the exact solution when t is given, okay? So it's not the training data. So this black true line is the line, the exact solution line. So the line represents this equation, okay? This exact solution equation, okay? Although we could have just used our hands to solve this problem, but I'm just showing that this physics-informed neural network successfully predicted the equation itself by using only 30 points, okay? Okay, so this is like a TensorFlow version for the physics-informed neural network. So this might be very hard for you because there's very many mathematics or even physics afterwards. So just the key point here is PINN can just predict exact solution when the problem is related to the physics, okay? And when we have mathematical equation of given points, okay? So as I said again, not only with TensorFlow, but also a new library called DeepXDE can be used to perform the PINN, okay? So DeepXDE library has a various supporting backends. So TensorFlow 1, TensorFlow 2, and PyTorch as a backends. So since we have used TensorFlow 2 for this entire course, so we're gonna just set our backend as a TensorFlow. And if you want to use TensorFlow 1, then just follow this kind of warning statement. And if you are familiar with PyTorch, just type it PyTorch. So backend is just how to compute the gradients were like this, okay? So this backend, it's not that important, but we're going to use TensorFlow 2 for this problem. So the same problem we're going to solve as previously taught example with TensorFlow. Now we're going to use the same exact problem with dibxde, okay? So importing library is the same, but we have another dibxde import as a DDE, okay? And for the ODE system, in the previously defined TensorFlow version, we use gradient tape and very different kinds of equations. For example, let's see here. Yeah, this ODE system, the same equation was like 20 lines long, and you need to just use the gradient tape for because TensorFlow just removed its automatically calculated gradients. But dibxde just made it simple. Just one line is used for the ODE system, okay? So du under by t is du over dt is a Jacobian matrix over u and t. So Jacobian matrix is same as du over dt and is defined in the dibxde program. So this term is basically the ODE loss that we discussed before, right? This is the ground truth equation that we know, and du over dt is the points that our network will predict. Okay, so we need to use gradient tapes and other things for the TensorFlow, but for the dibxde, simple one line is just good, okay? So for the dibxde, you need to define three things. First is the system. This system is ODE system. Second, initial or boundary condition. Third is to define the geometry, okay? So we need to define these three things before we do the dibxde, okay? So we define the ODE system. Now this is initial condition. This initial condition or boundary condition is quite simple, okay? It is not changed from this any codes, okay? You can just memorize the code or just use this code because it will not change, okay? So it basically tells us if t given in this function is in the boundary or initial condition, we will get this t as a value of 0. So it means that it will return true or false so that we can know that specific point is an initial point or boundary point or not, okay? This function just returns true and false so that we can find out that specific given point is a boundary or not, okay? This is just a boundary decider, if you want to say. And for the geometric part, so this geometry means like some kind of physical dimensions or something like that. But this time, because we're not dealing with any physical things, we're just dealing with time, right? So we're gonna just define the geometry with a time domain of between 0 and 2, okay? And in order to define the initial condition, we will use this initial condition, or IC, and we will say that in the initial condition, it is equal to 1. And this boundary function is given above. So this means that if t is met with the boundary or initial condition, then just return 1, okay? So this function is just deciding the initial condition. Or you can say that if the model predicted u is a u hat, then u hat over 0 is basically the IC, okay? And we want this friend go to 1 so that we can minimize the initial condition loss. And because we know the true solution of this problem, we define the true solution like this. But if we do not know the true solution, it is okay to just skip the true solution, okay? So this is the final stage that we want to aggregate all the information we defined above to single variable data. So as I said, we need three things for the dibxde. First, system, an initial condition or boundary condition, and geometric information. And this number of a domain means how many collocation points will you use for this task. As I mentioned again, the collocation point is, you can think as a training data, but it's not kind of training data because it can change randomly, okay? You can just randomly choose any t, so it's not gonna be same for every step, okay? And because we know the true solution, we set solution as true solution, but if we do not have any true solution, we can just remove this line. And let's define the network and the hyperparameters. So as a network, we said there is only one hidden layer with 32 nodes. So layer size is 1, 32 plus 1, okay? This is quite simple, but because you don't have to use TensorFlow sequential into like dense layers, we don't have to do that. Just define the layer size and activation function you're going to use, or even the initializer that you want to use. This initializer we haven't learned during the class, so you don't have to worry about this initialization. So with this FNN function in the DDE, so which DBXDE, there's FNN function, which means fully connected neural network. So it's equal to dense layer, but we have defined the layer size here, and activation here, and initializer here. So with this simple function, you cannot just build a total ANN model that we will use for this problem. It's much short code because DBXDE is basically for the PINN itself. So we're going to compile the model with Adam Optimizer, okay? And we're going to train the model we defined above with the data that we defined for the 6,000 iterations, and let's see the results. So there's a train loss here. So first loss is the ODE loss that we defined, and second loss is the initial condition loss. So this loss term is separately calculated and will be squared and averaged afterwards, okay? And I didn't mention that we also here had a test data set given so that we can get the test accuracy as well. However, this is not necessary for any cases. So I'm going to skip this. And we can see the training loss also decreased very well. And also, as you can see in the results section, we can see that our PINN just perfectly predicted the function, the exact solution as shown here. Okay. So now this PINN is just used as some kind of differential equation solver for this problem, but we can solve much harder problems with this neural network. Now we're going to go on some kind of solid mechanics. So I'm not going to talk about details about mechanical engineering or solid mechanics because I know the half of you guys are not from the mechanical engineering background. So I'm going to just briefly explain the problem and just keep going. So the Euler beam itself is just, you can think as a beam that is that's stuck into a wall. And if you give the uniform pressure on the beam, then the beam will bend, right? So if there's a wall here and there's a beam, and if you give the uniform pressure on the top of the beam, then the beam will deform like this, okay? In this problem, we want to find how the elongation distance at each point x, okay? This is x direction, and this is y direction, okay? So we want to find, like, when x is equal to 10, how many elongation we have at y direction. So this is the question we want to solve. So basic properties are given like this, and this kind of situation can be solved by this partial differential equation. Does have a fourth order of the differential equation, so it's quite complicated equation. And there are 4 boundary conditions defined here because we have fourth order of differential equation. So there's a Neumann boundary condition, and there's a two other boundary conditions, but I'm not going to just explain what this boundary condition means, but you can just think as an initial condition as given before, okay? Just take it as a boundary condition or initial condition. And I can be sure that there will be no problems in homework or final exam that requires that kind of like solid mechanics knowledge or like that, okay? There will be no problems like that. So you can just watch and just use for your own domain later on. So again, we have PDE system and 4 boundary conditions for this question. So also these have exact solution. We can calculate the exact solution for the PDE problem like this. But we do not have to have this exact solution to perform the physics-informed neural network. Okay. Now let's begin with the model. So since our problem right now is much more complicated than before, we will use more hidden layers, 3 hidden layers this time, and also the rest of things are very similar. However, we have different governing equation and different boundary condition compared to before, but it's quite similar. We use the mean squared error between the predicted value and the governing equation value. But since we can predict UX from UX, and we only know about this kind of solution. So U here is Y, okay? We have governing equation like this, but we have only this, okay? But we want to compare this UX, whether in order to perform the arrow backpropagation, we need to perform 4th differential order onto these equations so that we can compare these two, okay? So importing library is simple as before. And this is, we need to define the PDE system, but PDE system is defined over here, okay? So if you see this, and this is, DDY goes into Hessian. Hessian is basically the 2nd order differential equation between X and Y. Yep. So basically, we do not have the 4th order differential equation for defined in the equation. So we need to do Hessian twice. So if you want to get like this equation, then you need to have 2. So basically, Hessian matrix going into the Hessian function will return the 4th order of the differential equation because Hessian itself is a 2nd order, okay? 2nd order differential twice is 4th order differential, okay? So this is basically returns the PDE function that we have. So this here is equal to the equation here. But since we know that this function needs to go to 0, we will use just this function as a lowest term, okay? The last time we knew about, we compare between the predicted value minuses the true value. However, for this problem, we know that the predicted value should go to 0, so we do not need this minus term. So we just defined here, just return this, and this should go to 0. So this term itself becomes a lowest term, okay? And as I said again, the boundary definition is always simple, okay? It's just always same, okay? For the last problem, we defined the boundary as an initial condition, but for this problem, we will define the boundary on the left side and the right side. So this is just returning a true or false value if the left side is, if the point is in the left side boundary or the right side boundary, okay? And we will define the geometry here. As I said again, we need to define three things for the DBXD: geometry, system, and boundary conditions, okay? And we defined the boundary condition and PDE system before, so we're gonna define the geometry we will use for this problem, okay? Now I said our beam that is stuck in the wall, okay? But we will not consider about the thickness of this beam because it is unnecessary. So we want to just consider this length of the beam, okay? So the length, because we are considering only just in x direction, we're going to just use interval between 0 to 1. So in the problem, we have given the initial condition of L is equal to 1. So the length of the beam is equal to 1. So our geometry is simply, if you want to consider it as just a line in 1 meter distance, okay? So now we've defined the geometries, and we will define the 4 boundary condition. And again, this kind of boundary condition decider are not necessary for this class, okay? Just, yeah. We will give, if we are just, we are making homework or for the exam, we will make sure to give this kind of information, and you can just code the whatever network with hyperparameters, okay? So you don't have to worry about this. So boundary conditions are given like this, and you don't have to worry about this. And true solution, we know the true solution, but so we define this. And as I mentioned again, we're going to just aggregate all the information that defined. So the geometry, the system, and 4 boundary condition we have for this problem, and number of domain, which is also equal to the collocation points, and 10 points will be used for this collocation point. And also, because we know about the true solution, we will define solution as true solution here. So for the layer definition, so as you did again, so you had to define 3 things for here: layer size, activation, and initializer. It's same, okay? And we will always use fully connected neural network, so you can just plug in the right things you want, okay? It's quite simple. And for this problem, we're gonna use 5,000 epochs to train the model, and let's see the result here, okay? And if you see the loss term, there's 5 loss term. So this 5 means first is just a PDE loss, and the rest of 4 things are boundary condition loss. Remember, we have 4 boundaries, so we have 4 boundary losses, okay? So this is like PDE loss and 4 boundary loss. And this is test loss if you have test data set, but if you don't have test data set, you don't get this test loss. So just this train loss is important here. So our train and test loss converge very well, and let's see the results. Okay, with this collocation, 10 collocation points, our physics-informed neural network model successfully predicted the so the elongation of the beam given in the x direction. So with this simple 10 points of the information, we just predicted how this beam will react to the given force, okay? Normally you need to, like for this problem, you can just solve by hand, but for a harder problem, you need to get data and just do the perform solver. It's like a differential equation solver that takes a lot of time and computation costs. But for the physics-informed neural network, you need just 10 points and a physics and equation to solve this problem, okay? So, yep, our physics neural network performed very well for the simple Euler-Beam equation as well. So, yep. So there is fluid mechanics example as well, but I'm not going to discuss this over here because it's quite complicated. So, and we are running out of time. So any questions about physics-informed neural network? Any codes? But you don't. I know this kind of seems very hard because we are simply using a new library called deepxd, but you do not have to worry about deepxd. I think we will not gonna make question that requires deepxd. This is just an example to show you how to use deepxd and physics-informed neural network. So if you guys do not have any question, I have a last word I want you guys to take home for the physics-informed neural network. So when you have a small number of data, but you have a mathematical or physical equations or physics behind them, PINN and physics-informed neural network may be the answer, because with very little of data, you will not be able to train this neural network. For example, if we have 10 data and we stack 5 hidden layers, the layers will simply overfit it, right? But with the physics term at the loss, we will be able to predict the right and exact solution that we want before. So if you have data and the data has physics behind them, maybe the physics-informed neural network can be the answer for you. Okay? If you guys don't have any questions, then let's end the class here.